let's finish up chapter the section 8.4. Just adds on a few more applications. These ones not being as big, significant, but it won't take as long to set up. So first, economics. So I'm going to mention this idea of consumer surplus real fast. The problem is also talk about called producer surplus, which is just like in the problem. So it's just an interesting thing to kind of read for yourself. But at least for this, we're just going to kind of present it. So when you take an economics class at any point, obviously one of the biggest things you talk about is a supply and demand curve. Which changes depending on the object, where the demand curve is going to look something like this, and the supply curve would be upwards. Essentially saying that this is kind of the dollar amount in this case, and this is going to represent the number of people. Or sorry, this is the dollar amount, and this is the number of people. So this is dollar amount, and this is number, right? So on the demand curve, right? Obviously, if you have a product, right, and it's at a pretty low price, right, then the demand for it's going to be pretty high because it's still, they want it, right? It's a low price, so they're willing to buy it. But as you move along and make your price bigger, right, the demand for that is going to shrink, right? Because no one's going to want to buy it at that much of a price. So that's why the demand curve goes down. However, right, the supply curve goes the opposite, right? Because if they're only going to make this much off of it, no one's really going to want to supply it or produce it, right? But as it shifts up, more people are going to want to, hey, I want to part of this. I want to, make money off of that. So they just kind of go in opposite direction, right? In terms of supply and demand. But there's a sweet spot, right? Which is right here, right? And the book marks the spot, or as P. Okay. And for the sake of this discussion, we won't worry about the supply curve as much. But this P is going to be that spot where they intersect each other. We're kind of the match counts essentially before it. They kind of move over in each spot, right where the one to supply is less, but there's a lot of consumers that are wanting to buy them. Now, we have an interest to understand in this area, right, what the surplus of consumers is in this spot, right? Basically, what's right, because we know that this is sort of like the sweet spot of people, right? The same amount of people demanding is there is supplying it. When we're in this area, right? What is this kind of? It's just it's the difference. I'll read what the book says. It says the difference between what a consumer is willing to pay and what the consumer actually pays for a good is called consumer surplus. So that's what this area on the graph represents. If we're interested to know what this is, in order to glean something from it or to gain something from it. And the way that we do that, right, is that we have this curve, which is we're gonna call P of X. Right. Again, you have a certain dollar amount, and you're going to have a certain number of people. So if I want to find the area of this, right, you can take all the rectangles and add it up again and find this, right? But we know how to get the area of this curve. The area of this curve, right? I don't want to just do P of X, right? My goal, I can't just do from A to B or from 0 to B in this case of P of X. Because that would be everything under here, but I don't care about everything under there. I care about everything up to this sweet spot. So we're going to take P of X minus P dx. And whatever the value of this integral is, is going to be the consumer surplus. Okay, so just a quick setup. Yeah, zero or that should be zero, just because where your starting amount should be at zero in all cases. So, and they use, I guess instead of B, they use a big X, but it doesn't really matter. Right? We start at zero and we go to X, which is X marks the spot, which is the sweet spot. Okay, so for example, let's see if we can see if there's a. So they give that in number 4, for example, that the demand function for a particular vacation package is going to be P of X equal to 2,000 minus 46 times the square root of X. So interesting how someone got that, but regardless. And we also are given that the sales level, which that's what this P means, it's called sales level. That price P, yeah, which is that perfect spot. Let's see. Oh, I see. Okay. Actually, the sales level is actually going to be our X. So the sales level in this case is 400. Okay, so we're given this X value and we're given P of X, and we want to know what this consumer surplus is going to be, which is going to be right. So we're given X is 400 for this problem. Now, I need to figure out what P is first in order to plug things in, right? Is there some way that I can find this P value, given the P of X function and given what X is supposed to be? Yeah, just plug the X in, right? So we're going to get, so P, the big P is going to be P of 400,000 minus 46 times the square root of 400. The square root of 400 is going to be 20. 20 times 46. Let's see. 920. So we get 2,000 minus 920, which is 1,000 each. Right? So from here, your integral just becomes, you go from 0 to 400 of 2,000 minus 46 root X minus 1,080. 2,000. Or I can rewrite this as, since 2,000 minus 1,080, I can do 9. Which this we can totally do. Okay, so here it's really simple, just kind of plugging in. Just put in. So if it talks about sales level, talk about 400. If it gives you a specific sort of price, that's what P you're going to be given, and it's going to give you the P of X, kind of the demand curve. That's what it represents. Okay, does that make sense? Okay, so that's consumer surplus. The book also talks about producer surplus in the problem, so I think I assigned something like that. So I would encourage you to. Okay. Concerns blood flow. So earlier on in the book, it says example 2.7.7 to be exact. You learn that the law of laminar flow is going to be the equation P over 4 mu L. Again, these are going to be, obviously they'll give you a lot of these values plugging in. Which tells you the velocity that flows, like that's going to flow on the blood vessels with a certain radius, right, and a length. That's going to be a distance r away from kind of your central axis in terms of the tube that you're going through. And then N has like a certain viscosity of the blood. So for different, whatever we're talking about, right, the blood flow. Yeah. In this case, the problem's interested in finding kind of, we want to study a little bit more about this. We want to find the flux of the blood flow. So to do that, we're going to take, we ultimately want to take this velocity. We're going to multiply it by, let's see. Okay, gotcha. So we're wanting to ultimately find this thing called flux, which is going to be the volume per unit time, or the rate of the flow. Right. So we know the velocity given how far you are away, but we want to know, just given how large, how big this radius is, if we could just find a general formula for it. So we take this formula and we're going to get kind of the area of the ring in general, which we're going to approximate. If I have a ring this size, okay, I can approximate this thing, the area of this thing, just of the ring. Don't need to worry about the thickness or anything, by cutting it and then stretching it out like a rectangle, kind of similar to what we talked about a little bit yesterday, and saying, okay, well, the radius, it has some radius, which we'll call Ri, right? Because it may shrink as it goes through, but we'll call this one Ri here. The circumference is going to be 2 pi Ri, and we're going to get delta R for the thickness. And so the area is going to be approximately 2 pi Ri times this delta R. And from this point, right, this is going to be the area of the ring, right? And the velocity we have is working in units of like distance, which I'll just write meters per second in a way. But it may not be meters, it may be feet. But we're kind of taking a meter squared and multiply meters per second to give us an overall volume per second. So what we can do with this, right? Again, I want to multiply them together. And as the ring size changes as we move, we're going to add up all of our different components. So we're going to have I equals 1 to n, and we're going to take 2 pi Ri delta R, and we're going to multiply it by this V of R here. Okay, but we want to take this, obviously we want to approximate as good as possible, so we're going to take the limit as we go all the way towards infinity. Okay, which I can take this and write this as an integral, which is going to be the integral. Now in this case, again, our radius is the thing that's varying. So I'm going to go from the innermost smallest radius, which is 0, to the outermost, which is this R. And we're going to have 2 pi R, right? Just change the Ri to R, and this R right here will be an R as well. So we're going to have VR, so we're going to have P over 4 nu L times R squared minus R squared dr, right? So then we work out this integral, and we're going to have, let's pull out everything we can. So all of these are constants. So we're going to get, let's see, the 2 and the 4 are going to cancel a little bit. We're going to get pi P over 2 new, which is just like, okay, it's a little under there. L, and then this is going to be the integral from 0 to r of r squared r minus r cubed. But we can integrate both of these, which just this part we'll focus on. We're going to get 1/2 r squared, little r squared, minus 1/4 r to the 4th power from 0 to r, thus giving us 1/2 r to the 4th power minus 1/4 r to the 4th power, which is just going to leave us with 1/2 minus 1/4, which is still 1/4. So in the end, I have this times 1/4 r to the 4th, which will leave us with pi p over 8, sorry, r to the 4th over 8. And this is equal to that. Okay, so we can actually use all of our knowledge to, again, using integrals to take this knowledge of, okay, this is how fast the blood's moving. Can I figure out the different ring sizes as I'm going through and add all those up to get the approximate volume per unit time? We can't. Just using integral techniques, taking some approximations, taking the limit as we go towards infinity, we can do it with that equation. Okay, so I think if anything, there might be a problem where you would just have to plug into that. But again, just wanted to show an application here for this guy. Any questions on the work here? No? Okay, good. Finally, we have what's called cardiac output. Again, these last two were more biology, right? So the cardiac output, because you won't have to do a problem really. Volume. Volume of blood pumped by heart per or it says the rate of flow into the aorta of the heart, not for anything. That's just how much blood is being pumped by the heart. So we have a method to calculate this, calculate this cardiac output, called the dye dilution method, which essentially says that so here it is. Okay, so what happens in this case is you insert a probe of sorts to measure this, and it's going to be measured over a certain amount of time, a certain interval, which goes from 0 to some time t, right? Until, so they put the dye in there to measure it, and then it's going to be this time t when it's finally cleared out as it's run its course. C of t we have is concentration. Okay. That we're putting into body in order to measure this, of course. And we're going to divide, let's see, concentration of dye at time t. Okay. And then we can take this interval, right, and we're gonna cut it up, right? We're gonna do all of the separate little intervals, just like we did, to kind of do it in smaller parts, not just take the one big part. Then what we're gonna have is the amount of dye that's gonna flow from time between the two times, like that we split those into. So let's say we have a time between Ti minus 1 and Ti. Between this interval, we're going to approximate that by taking the concentration of the dye at time t times the volume, which is going to be flux, right? Again, we're going to calculate this different way, but still a similar idea, seeing how much we flow out, and then this is going to be times right? Because if I take the flux, which was already in meters cubed per second, multiply it, this gives me my volume. And so this is going to tell me the amount of dye. Okay, but right, this is just for this interval. So I want to take this and add it up together. So I'm going to put this into a sum, right? This is just like AI, let's say, and this is CTI at that current moment. So we want to take the sum. So we want to find A total, which is going to be the sum of F of C of TI delta T. Like that. Which F should be a constant, as it is over there, which we can calculate. So I'm going to pull it out, and this should be provided. So A F the sum for my one in of C of Ti. That's T. But of course, we can take the limit of this to get the exact value. So I'm going to take the limit as n approaches infinity. And so this is going to be integral of, and this will be from 0 to t, of C of T. Okay, but in the end, we didn't want to know the amount of dye, right? I didn't care about that. I ultimately wanted to know what the volume of the blood pump is of the heart per unit time was, which is what this F is going to be, similar to what the F was over there. So in the end, I'm going to get F is equal to A over the integral from 0 to t. And this will be my okay. Good. So we have an example. I think I only end up giving you one problem like this, so there's not really reasons to do that. So I don't really want to spoil it. But simply, they would give you C of T, and then you plug it in, you integrate this. They're also going to give you this amount, and so you just divide it. Okay, so really, a lot of words to say. I mean, these formulas are pretty easy to plug into, right? You get to do the easy part of just using what you have, right? They give you the numbers. You want to know what the cardiac output is going to be. You just use this formula. If you want to know what the consumer surplus is, then you use the P of T minus P. So, any questions there? Yeah, sorry to feel a little rushed. I just wanted to go ahead and wrap up this section just because don't need to spend too much time on it. Again, the homework should be pretty straightforward. Just use the formula. This one, use the formula. That's all it is. Okay. Anything else for me? Other than that, we're good. I'll probably go ahead and stop the video here. But for anyone to discuss the hydrostatic problems or anything, we can do that. I don't mind. There's a bit of time. You're good to go. We'll start chapter 9 tomorrow.